this session, again under robust design and Taguchi method, I will be referring to one particular aspect, very important aspect, that is classification of the parameters and the quality evaluations. Okay, so these are the two topics we are going to discuss in this session. And so the question remains that you have probably understood by this time that if you want to apply the Taguchi method to create a robust product, now you should be knowing the performance of the product with respect to various possible conditions. And when you start producing the product with respect to or in a process or using a number of processes, now what are the factors, what are the parameters affecting the output quality characteristic of the product, you must be able to identify first, and then you must suggest the settings of these all important or all the relevant parameters or the factors of the process. So, and there could be in a particular case there could be many types of parameters. So, the first thing you need to do, that means you need to identify the process parameters, relevant process parameters, and you must be able to classify them. So, how do you classify them? A schematic representation of a product or a process is shown in a figure. So, I will show you that figure, and what you find in this figure, the response is denoted by Y and is called the quality characteristic. This is always we use the term quality characteristics. The parameters that influence the quality characteristic are classified as follows, and these parameters are sometimes referred to as the process parameters. Okay. So, the first the term we use, that is the signal factor. Notation is M. Okay. The Taguchi has used a term called signal, and he has proposed a performance measure called signal to noise. So, we'll be elaborating on that later on, okay, in another lecture sessions. So, you also must know what is this signal factor. These are the parameters set by the user or operator of the product to express the intended value for the response, okay, of the product based on the knowledge of the product being developed. So, that is the signal factor. That means this is the intended value of the response. That means you can identify several output quality characteristics. They are also referred to as the response variable or the responses, simply responses, output responses. And the signal factor means you prescribe values for all those output quality characteristics in plain and simple terms. Sometimes two or more signal factors may also be used in combination to express the desired response. Is it okay? So, depending on what type of product you are designing. Okay. Next one is the noise factors. This term we have been using, and these noise factors can be of two types: internal noise factor as well as the external noise factors. We have already cited several examples of these noise factors. Notation is X. Certain parameters are not controllable by the designer and are known as noise factors. That means these are sometimes referred to as uncontrollable noise factors. Parameters whose settings, also called the levels. Is it okay? There is another term we use when we discussed the design of experiments. Obviously, we use the term called levels. So, we are already aware of what is a level. So, parameters whose settings or levels are difficult to control in the field or whose levels are expensive to control are also considered noise factors. like say ambient temperature or say the humidity in a given context. Suppose they are difficult to control. Okay, so what do? You say that these are, I am considering them as the noise factors. The levels of the noise factors change from one unit to another, from one environment to another, and from time to time. Is it okay? So this is known. There are several examples. The noise factors cause the response y to deviate from the target specified by the single factor m. That means value of m will be affected and lead to quality loss. It's clear. So against each quality characteristics there is a signal. You have to specify. You as a designer, you must be able to specify, and then you check that what are the noise factors that may be affecting the value of m or the value of the signal. Okay, so at any point in time, you know that these are the set of noise factors, like say like humidity, the temperature, the dust, fumes, etc., etc. So there are many examples. What are the control factors? The notation is Z. These are the parameters that can be specified by the designer, like say in a typical say the machining operation, the turning operation. Is it okay? What you find that the spindle speed is very, very important. So you can control it, like say spindle speed by RPM. So you say that I have a settings of RPM that is between 500 to 700. That means any value between 500 and 700, including 500, including 700, any value is acceptable to you. So these are basically the control factors, or the feed rate, okay, for metal cutting operations, right? So there could be many control factors, and control factors can take multiple values called levels. Is it okay? Right? So this is the block diagram of a product or the process. So you must have in your mind this particular block diagram. So what is the block diagram? That means there is a product or the process. Whenever you talk about the process can be of one step or process can be of 100 steps. So from this product or the process, you expect the response. The notation is y. This process or the product performance is affected by several kinds of noise factors, both internal as well as the external type. There are the signal factors. Signal factors is like this, that is the m, and these are the control factors, that is z. Is it clear? So this is the block diagram of a product or the process. Now let us take one numerical examples so that you understand the whole concept more clearly. The critical dimension of a mechanical component made using a turning machine must be 0.45 plus minus 0.005 inches. Okay, so this is just one example. So this is the tolerance. The scrapping cost is $100 per component. Samples taken from the turning machine had the following dimensions. As I have been telling you that for assessing the loss or for measuring the loss, what you need to do, you have to collect data on y, and so these data points, that means the possible this value of y will vary. It is expected to vary from one unit to another. So these values you consider. You have collected these data points 0.451, 0.447, 0.448, okay, 0.452 and so on. Is it okay? So how many data points you have considered? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is the sample size. So this data set you have collected. Find the Taguchi loss equation for this operation. Is it okay? That is the first question. And the second question is determine the average loss function for the parts made using this turning machine. Okay. So, how do you get the solution? The first question is Ly, you need to calculate. So, it is a case means you are dealing with a quality characteristics, and this quality characteristic is nominal is the best type or the target is the best type. So, you use this formula, that is Ly equals to k into y minus m square. We have already referred to this particular formula, and we know the expressions for small k, that is the proportionality constant, that is capital A divided by capital delta square. Is it okay? So, what is capital delta? Capital delta, that is the limit of the deviation, that means the deviation from m, and the corresponding loss is capital A. So, capital A, the value of capital A is 100, already this value is given. Okay, they have already estimated. So, this is an estimated value, and this deviation is 0.005. Is it okay? Because the tolerance is 0.45 plus minus 0.005. So, this is an extreme point. So, if the value touches this one, that means the deviation is plus delta or deviation is minus delta. So, the actual value is 0.005 square y minus m. That means this value is 4 into 10 to the power minus 6 into y minus square. Now, how do you calculate this y minus m square? That means you have considered all these 12 values. Is it okay? And you consider their the sample mean. So, the population mean is approximated with the sample mean, that is x bar. So, the 12 values you have taken. So, all these values you add and divided by 12, you get a value of 0.451, and then you calculate the standard deviation. The notation is sigma. Is it okay? It is basically a sample standard deviation. So, it is sigma hat. So, root over 1 upon n minus 1 sigma yi minus mu whole square I equals to 1 to 12. Is it okay? So, this is the total value you have computed in the square terms, and ultimately you get a value of 0.00286. So, you are required to compute these values independently. It is very simple in fact, and then you get the value of the quality loss, the average quality loss. That means this is the value of, say, this proportionality constant, and then what you do, that means 0.451 minus 0.450, that is the deviation, and the square plus this one 0.00286. okay, that is the square deviation. So, you apply this formula, ultimately it becomes 36.72. average quality loss is equals to 36.72. Is it okay? So, the first part is understood, and the second part is also, you just follow the steps and you will get the value of the average quality loss. So, this is a typical numerical problem, okay, at the very first stage. Now, quality, when you try to evaluate the quality, obviously right at this stage you must be aware of that this evaluation must be based on the quality loss. According to the traditional concept of loss function, that as long as the product's quality characteristic is within the specification limits. Now, these aspects to be understood very clearly, or tolerances, there are no losses incurred. That means what we are saying, that we are specifying the tolerance range, and as per the traditional concept, what we believe in, that any value you get within this tolerance range, it is acceptable to you, and as it is acceptable to you, as per the tolerance range specified, there is no quality loss, and any value within this range will have the same impact or the same loss incurred, and you assume that this loss is held at very minimum. Now this loss takes the form of a step function with a constant value a outside of the specification limit or the tolerances. Is it okay? Now this I am going to elaborate with a figure later on. Okay. So loss function Ly makes no distinction between products whose quality characteristics is exactly on target at M, okay, or whose quality characteristic is just above lower specification limit, or whose quality characteristics just below the upper specification limit. Is it okay? So just three cases we have specified. That means a value you get, it's absolutely around or is very near to M. Another value you get, that is it is less than LSL, but is almost touching LSL, lower specification limit or lower tolerance limit. And the third value you get, that is definitely it has not crossed USL, but it is very near to USL. Now as per the traditional concept, all these 3 points are considered the same, identical. Is it okay? But actually they are not. Now these aspect, that means this traditional, whenever you believe in the concept of say Taguchi loss function, so obviously the traditional concept is not applicable. So the traditional loss functions, that means this is your target value, this is the quality characteristics of y, whether the value you get over here, the value of y, or here, so long, or here very near to M, so long they are within this range, okay, we will assume that there is no loss, or even if there is a loss, that means this will be just minimum level. But as soon as it crosses this value, or in sometimes no, if it touches this value, that means this is the value almost is on say M plus delta, okay, on the limiting value. You will find that we say that there is a loss, and this loss will continue, and this loss amount is A. So whether the deviation, so whether the point is here or here, you will assume that the loss remains same. Okay. So this is the traditional loss function. Now is it acceptable to you as per Taguchi philosophy? Taguchi says it is not acceptable. Our goal is that you need to produce as far as possible, or in as many units as possible, you need to produce the values around M. Okay. It is best if you can produce at M, but because of some reason, suppose you cannot reach the target all the time, at least the value you get, its deviation from the M should be as minimum as possible. Okay. So if you have, and then you have the quadratic loss function, as you deviate more from say the target value, obviously you will be incurring more loss. It is not that it remains same till you reach say the limiting value, that is the upper specification limit or the lower specification limit, and if you cross this value, immediately the loss shoots up to A. That means is a loss, is a step function you assume. Okay. So in majority of the cases, this sort of the step function approach is not valid. So how do you evaluate quality? It is also doubtful that the loss function Ly remains constant at a value of A beyond the specification limits USL and LSL. Since the Taguchi loss function increases quadratically with increasing deviation from the target value, the Taguchi loss function can be applied to 3 different situations or cases, namely target is best, smaller is better, larger is better. Is it okay? In the target is the best, or the nominal is the best case, the measured response y always has a specific target value M. Then the quality loss is undesirable on either side of the target. The quality loss increases in a quadratic manner as the quality characteristic deviates from the target value. That is why it is referred to as a quadratic loss function. Examples of quality characteristics. Now we are referring to the examples of quality characteristics of the target is the best or the nominal is the best category. Product's component measurements such as diameter, thickness, length, a product's quality characteristics such as the properties of a fluid, etc. The nominal, the best loss function can be applied to just one part or a product or to the average loss associated with more than 1 units. Okay. So, this is the equation. So, we have already gone through, again we are revising this one. So, a proportionality constant called the quality loss coefficient, that is K, M is the target value, Y the value of the quality characteristics, Ly is the loss in dollars when the quality characteristics is equal to Y. Note that Ly equals to 0 when Y equals to M. So, this is the way you calculate this. So, the functional tolerance range of the quality characteristics is M minus delta and M plus delta, and which represents the maximum permissible variation. If the consumer's average loss is A, when the quality characteristic is at the limit of the functional tolerances, okay, then A represents the customer cost for repair or replacement of the product. So, the proportionality constant is obtained by this, is already we have computed, and then Ly is this one. Okay. So, Ly is A divided by delta square into Y minus M square. So, expected loss is the mean loss over many instances of the product. The expectation is taken with respect to the distribution of the quality characteristics Y. Already I have mentioned. The average quality loss is obtained by considering an average of the measure of the off target performance Y minus M square of the loss function. The deviation referred to is from the target value M. So, average loss function Ly bar is equals to K into MSD. Okay. So, always remember this particular the formula. Ultimately, we have derived this formula. What is MSD? That means as mean square deviation. So, we have expressions for mean square deviation for the two cases. One is the nominal is the best or the target is the best, and the smaller is better. Okay. So, this is the expressions we have. So, you have n number of the data points for the given quality characteristics. So, each one is compared with M, and the deviation is squared, and all these squared deviations are added. So, you get these expressions in fact. So, sample mean is this, already you have computed, 1 upon n sigma yi I equals to 1 to n number of data points. So, how do you compute the MSDs? So, you apply this formula. Okay. So, mean square deviation is given by this expression. Is it okay? So, this is y bar minus m. That means, this is a sample mean, and how the sample mean is deviating, okay, is different from the target. This is the one part, and the first part is the individual values, how the individual values are different from say the average value or the mean value, that is y bar. Is it okay? So, if the target is the best or the nominal is the best case we consider, then MSD is given by this. So, what is it? That means the average square deviation from the mean, average square deviations from the mean, and the square of the deviation of the mean from the target value, that is this one. So, this is population standard deviation and the squared bias of y. So, this is referred as the squared bias of y. So, this is variance of y and this is the squared bias of y. Okay. So, you have this expression, that means the sigma square plus y bar minus m square. Is it okay? Also, for n is greater than 30, that means for the large sample size, the sample variance S square is approximately population variance sigma square. So, that is many a time we assume this, but if the sample size is the small sample size, then you need to, in many cases you need to use some other the techniques whether it is parametric or non-parametric, that you need to consider. But maybe there will be always some variations, or you may go for some empirical study. Hence, the loss function for n units is this. Is it okay? Right. So, this is mu minus m square. So, k into a square plus mu minus m square, right. So, you refer to equation 6. To minimize the loss, MSD must be minimized. Okay, that is your main target, that is your main objective. This can be achieved by either minimizing S square, that is the sample variance, that is reducing the variability, that is causing the deviation of the data from, or by adjusting the average response to coincide with the target value m, that is y minus m square should be equals to 0. Okay. So, that means if you achieve this condition, that is the best conditions you have achieved. It's clear. So, if you can do that, that means what you are saying here, that means all the averages values, okay, average values are falling on say m. So, obviously that is the best possible situation, right. And but prior to that, you need to consider, is it okay, the variance also. That means the variability should be under control. That is the first exercise you do, and then when the variability is under control, then you try to control the value of mean. So, exactly this thing we do when we use the control charting. If you refer to the variables control charting, like when you refer to say R chart as well as X bar chart. So, first you try to control the variability of the process with the help of the R chart, and when you are successful in reducing the variability of the process, and then you try to control the process mean. Is it okay? Now, here is one particular case where you will find that your performance is like this. Suppose 10,000 units you have produced at your plant, and you will find that the distribution is like this. This is your plant. So, suppose a plant B, and plant A, there it is also using the same the specification limits, but its performance is like this, plant A. Now, the question is, which one is better from the quality loss point of view? So, this is the question is raised. Now, how to say respond to this particular question? Now, it should be noted here that the form of the distribution of the quality characteristic also has an influence on the expected loss. Is it okay? That means what you need to do, if the distribution is quality characteristic distribution is like this, what is you need to compute what is the expected loss. And if suppose with respect to the same specification limits for the same quality characteristics, you get this sort of the behavior or the performance, okay, then what is quality loss? Two typical probability distributions of a quality characteristic are shown in figure, where distribution A is a normal distribution, and distribution B is a uniform distribution, approximately uniform distribution. Okay. So, expected loss for the product from distribution A will be less than that for distribution B, since most of the product is tightly clustered around the target value for distribution A compared to that of the distribution B. Is it okay? That means the majority maybe 10 plus minus say 20% of the products. Is it okay? Or maybe say maximum 30% of the products, their values will be lying within plus minus 10% of the target value in case B, whereas in the case A, you may find that almost 70 to 80% of the values you will be getting within plus minus 10% deviation from the target value. So, obviously for say the situation A is much better than situation B. So, the standard deviation of distribution is about 1/6 of the tolerance equals to 10. The expected quality losses of products with similar functions can be evaluated collectively irrespective of their sizes or specifications using the above approach given by equation 6. Suppose that components of n different types are supplied to an assembly operation. Okay, so expected quality loss will be like this. Is it okay? So, please go through these expressions. In fact, this is just another derivation. Okay, when you deal with a number of components, and these components, one particular component is specified as I. So, losses due to deviations will be like this. So, one case is this, okay, I equals to 1 AI delta I square, and Ly will be Ki into this, right. So, Ki expressions will be this one. So, you need to compute item wise. Actually, you are doing it item wise, right. So, equation 7 gives an indication of the total quality of the product, and for many products, parts, elements and components, when a nominal size are preferred, we require to use the nominal, the best target or the best type. Bilateral tolerances, that means tolerances related to the basic dimensions given in the two directions plus and minus, are generally employed in this type of application. So, this example is another examples we have given. Okay, so please go through these examples again. We'll refer to these examples, right. Say the cost of repair. This is another examples of how to compute the quality loss function. So, I suggest that you just go through these examples. All the detailed steps are given over here. Is it okay? So, the basics we have understood. The issues related to the Taguchi method we will be discussing in the subsequent lecture sessions.